Okay, so good morning, everyone. Um, for today, I'll just continue, or this is a pre-recorded lecture, in view of face-to-face meeting tomorrow. I think there's been a call from USC that you extend you basically shift towards alternative method for the rest of the week because of the high heat index. Anyway, either way, I'll be out in another field work, so hence the pre-recorded lecture. Okay. So this is part three, chapter three rather, and second half of the chapter. So we just discussed yung textures associated with a contact metamorphism, uh, with its characteristic low pressure, high temperature gradients. So as we've discussed before, or the ending slide last time was that crystalloblastic series, which basically states that that the degree of or the texture rather of the mineral being either more euhedral or less euhedral is not a measure or is not a proxy for when the crystals crystallized or when what the sequence was the crystallization of the different minerals. So for example, some minerals like titanite, rutile, pyrite, or spinel, whether they crystallize first or they crystallize last, they will always be euhedral, whereas minerals like feldspar, quartz, and cordierite, even though they crystallize first or they crystallize last, they will always be least euhedral, or most likely they will be xenoblastic in texture. Okay? So hindi siya parang yung sa igneous plus dermal before. So euhedral not determined by crystallization sequence, but crystal property itself. So as a review ng effect ng na increasing metamorphic rate, specifically increasing temperature, recrystallization dominates, resulting to fewer relic textures and more recrystallized metamorphic texture, yung granophyll's na texture. Generally, you increase grain size in comparison to differential stress, with which decreases grain size, and you get straighter boundaries and less evidence of strain. Okay, so this is, by the way, cordierite. It looks like quartz. PPF in plain polarized light, it's colorless as well. In cross polarized light, it's low interference color. The main difference between quartz and cordierite is that if you look closely in these brown specks, those are actually radioactive minerals, or these are minerals containing radioactive elements. And as they decay, they leave behind these specks. Yan. The specks na brown na to, those are the markers ng radioactivity ng minerals na yan. One more thing, yung cordierite is constrained only in luminous. This is an luminous mineral, meaning it you don't expect it really in every metamorphic rock. You expect it only actually in specifically in low pressure over temperature metapelites and metasamites. Okay, so medyo special yung bulk as well as yung PT conditions for cordierite to form. So if you suspect that it's quartz and you're sure you're not looking at the metapelite or looking at a low PT metamorphic rock, contact metamorphic rock, most likely that is quartz. Okay, yeah. Okay. So some textures of contact metamorphism. Here you see in A, growth of new porphyroblasts. This is in B, this is basically uh, a pre-existing metasamite. Tapos meron siyang pre-existing foliation, as you can see from here. Pero after this basaltic dike intruded, itong texture na to, when we zoom in, is now recrystallized basically into granophyllous rock. These are Andalusite porphyroblasts. As you can see, they have no preferred orientation, which is an indicator for contact metamorphism. Yeah. So, ganyan yung itsura ng aluminosilicates in the field. In hand specimen, they are long and slender with cleavage planes, as you can see from here, perpendicular to or sub-perpendicular to the length direction. So, kung ito yung length direction niya, perpendicular dun yung cleavage plane. And then this is migmatite, a mixed rock. So, in white are basically melts. And as you can see, yung black naman, they have this tensional structures, which basically show the pathways, or which basically provided the pathway for the fell signals, as you can see from here. Yeah. So this all of these photos are from Hollister 2014. Okay, under the microscope, how do they look? They look like this. So this is PPL, or plain polarized light, on the left, and cross polarized light on the right. As you can see, ito yung sinabi ko kanina na originally it's may foliation siya na metasamite. So you can see it's quartz rich with a few biotite within brown and cordyite. Yan. And then after contact metamorphism, nawala na halos yung foliation and you get to crystallization. With ever increasing temperature, this will be recrystallized to coarser and coarser grains until eventually you end up with, for example, if you're already in the sanidinite species, sanidinite facies or the granulite facies, you can have a lot of these pyroxenes, as you can see from here. This is another granulophilic texture, as you can see clearly. It's yan. So these are biotite. This is olivine, and this is plagioclase, and this some amphiboles. So basically, it's a diba? If just looking at the mineralogy, you would think this is a gabbro, but actually, based on the texture, as you can see, and of course, based on field appearance or field occurrence, this is actually a granulite facies meta mafic. Okay, yeah. So hence also the very fine grained nature. So usually you get this fine grain texture kapag either you're starting from a really fine grained rock, so basalt, or you start from a highly deformed rock, shear zone, for example. Okay. Yeah, so those are the low PT gradient textures. Next, we move on to regional metamorphism. As I introduced before, regional metamorphism basically is a measure of metamorphism that's based on the amount of area, right? The large expanse that's been metamorphosed, yun ay regional metamorphism. So, hydrothermal metamorphism in seafloor, diba? Meron kang seafloor spreading center, so meron kang oceanic ridges, water seeps in, interacts with the rock that results to hydrothermal metamorphism. Since it occurs over a wide expanse, the whole oceanic seafloor is to a certain extent metamorphosed, specifically hydrothermally metamorphosed. That is actually another type of regional metamorphism. Okay? However, yung term or yung specific type of regional metamorphism that is usually associated with regional metamorphism is what we refer to as orogenic metamorphism. So orogenic metamorphism is actually the subtype, kumbaga, ng regional metamorphism, which is used sometimes interchangeably with regional metamorphism. So I hope you don't get confused. In textbooks, basically, pag tingnan nyo, pag sinabing regional metamorphism, it just talks about the area. Okay? Sometimes, unfortunately, na-interchange siya with orogenic metamorphism, which is, of course, of regional scale. Okay? So, subtype lang to siya. Okay. Anyway, orogenic metamorphism occurs in convergent plate margins. It's also known as dynamothermal type of metamorphism. Dynamo, or movement, and so pressure, and thermal, so temperature. So pressure and temperature, moderate pressure or high pressure, high temperature. So this is usually due to the interaction of plates. For example, here you have continental crust and an oceanic crust. The oceanic crust is here, as you can see, subducting beneath this oceanic crust and the leading edge of this continental crust. So as you can see, this interface, as we've discussed before, will experience high P, low T environment, so blue schists and eclogites. Whereas here at the back, you start forming volcanoes, you start upwelling, thinning of the crust and upwelling of mantle material, resulting to high T, moderate P. Hindi to low P kasi kung low P, dapat nasa surface na halos. Okay? This is moderate P pa din, moderate to high actually. So basically, what you have is an area of elevated temperature and an area of elevated pressure. So this complex process results to multiple deformation events with elevated temperatures, specifically at the back, resulting to highly foliated rocks with sometimes overprinting by contact metamorphism, both in the shallow level or in the even deeper level. So at this point, we have to talk about subduction initiation. There are two main types of subduction zones, what we refer to as Cordilleran type and Tethyan type. Cordilleran type is when you have basically oceanic interacting with continental material. So think of basically um, sino ba? Sa north, well, Pacific plate subducted beneath the Eurasian plate east in the west side of the Pacific plate. Sa east side naman, yung counterparts ni Pacific sa, ano to yung name ng plates, east of Pacific subducting beneath North America and South American plate, but it's the same process. You have oceanic material or oceanic lithosphere subducting beneath continental lithosphere. So that's Cordilleran type. When you have oceanic, that's a Tethyan type, right? So Tethyan type subduction zones would include, for example, yeah, Filipinas, for example. So you have the Philippine Mobile Belt, which is largely oceanic in nature, except of course for the North Palawan continental terrain. It's largely oceanic, which is a continental pala yung NPCT. The PMB yung sinasabi ko mostly oceanic, and it's interacting with Philippine Sea Plate, which is of course oceanic, and results to island arc magmatism. So that's Tethyan type. Okay, so what's the difference? Let's go first to the Tethyan type. So this is a model on how subduction may be initiated. You can have, for example, an older oceanic crust subducting beneath a new oceanic crust. And basically what happens is that so ganyan, pagbagsak ng old oceanic crust, although hindi siya necessarily old, so sometimes sabi may two model may well, depends on the author, but the prominent model is you have two ways. You have ito, induced or uh, spontaneous. So spontaneous is basically the slab is just dense. The one of the slabs is just denser than the other, so it just sinks, and it sinks. It's when it sinks, mantle upwells. So yung mantle material starts rising, and this results to magmatism. No need to the FABs and Bonninites afterwards, but this is too much for Geol 51. Ang point lang dito is that you basically have the subducting slab interacting with a very hot mantle material. And this very hot mantle material results to metamorphism dito sa subducting slab. So this is usually in the form, or this is usually preserved in the form of metamorphic sols. Okay, this is of course for an older oceanic crust subducted beneath a younger oceanic crust, yung spontaneous nga. But this can also happen in what we call spreading center reversals. Namot ako yung specific term. But anyway, this is spontaneous, right? Pwede rin siyang induced. Imagine, for example, you have a spreading center, oceanic spreading center, and then instead of spreading because of other tectonic processes, uh, the tensional stress changes into compressional stress. So what happens is that one of the slab, either this one or this one, has to go down. This time, pareha sila ng density, pareha silang bagong form lang. But because of compression, one of them has to go down, and that plate which goes down is then subjected to high P, high T, low P metamorphism. Take note, we're talking about low PT, so para siyang contact metamorphism. But this is, of course, para lang siyang contact metamorphism in terms of metamorphic gradient, but in terms of structures, in terms of why there is metamorphism, it's totally different. Again, the reason for the metamorphism in the subducting slab during the early subduction is that you have a very hot mantle material. So basically, para siyang plancha, ironing effect. So yung plancha, yung mantle natin, para siyang plancha, and in-heat niya basically yung subducting slab. Okay, eventually, of course, this is oceanic material. So this was basically at one point under the sea. So as it was basically under the sea or under seawater, the minerals comprising this slab have incorporated water into their structure. And as the subduction progresses and temperature increases, those fluids are actually released towards the mantle, and that cools down the system, the whole system. Okay, so that eventually, from something like this, low PT, you end up with something like this, high PT, high pressure, lower temperature. The lower temperature is again due to the fluids flooding the mantle and eventually, essentially cooling yung ating plancha. Okay? Yan. So this is subduction initiation. This is, of course, initiation pa lang to. After initiation, subduction can progress, and once it progresses, you basically lose the earlier records of low PT, and you end up with high PT na lang. Okay. Yeah. Um, so kanina, this is talking about the slab. So slabs. So you have oceanic and oceanic interaction. But what about here behind the oceanic convergence? So here you have basically mantle material upwelling and heating the surface, heating the shallower crustal materials, eventually leading to arc magmatism. Wait lang, right, sorry for that. So, sabi natin kanina, dito, this talks about the oceanic subduction. What about behind? So, what about this region na nakaka-encounter no elevated temperature and the pressure is not as bad or not as high as in the slab mantle interface? So, this region experiences yung ating, or this region is actually um, best recorded by the Barovian zones, yung type locality ng Barovian zones. So this is the Bukan, also known as Bukan zone in some uh, um, textbooks. So this is an exposure in the Scottish Highlands. So basically, it showcases increasing metamorphic grade and eventually leading to the granitic intrusion. So the granitic intrusions are not so obvious here, but anyway, you can see here the different zone, chlorite zone, followed by biotite zone, and then followed by garnet zone, andalusite zone, kyanite, and then sillimanite zone. So this is increasing metamorphic grade. So take note that the intrusions, this is not contact metamorphism, okay? Sabi ko kanina, increasing metamorphic grade papunta dun sa may intrusions, but the intrusions doesn't actually have anything to do with the metamorphism. Okay. What happened is that the upwelling of mantle material elevated the geothermal gradient in the region and therefore causing their metamorphism. Okay. The plutons are actually partially molten materials from the metamorphosed rocks. Some of the plutons at least. Okay. So it's not the granites which caused the metamorphism. It's actually the metamorphism which eventually resulted to granitic intrusions, di ba? So, hindi siya contact metamorphism in that sense. Okay? Yan. So, I hope that's clear. So, chlorite, biotite, garnet, staurolite, kyanite, and sillimanite zone, this is basically increasing metamorphic gradient. Again, remember at this point yung metamorphic field gradient that we've discussed before. Yan. Okay? So, these Barovian zones, again, we expect this only for metapelites, metamorphosed pelites, with increasing metamorphic grade. Okay, so this leads us to the concept of paired metamorphic belts. So we've discussed the subducting slab interacting with the interacting with the overriding plate, both the oceanic lithosphere and the other underlying mantle material that is experiencing high pressure, low temperature. So that's the four arc trench lithologies. So it's characterized by high P, low T environment, resulting to rocks such as blue schists and eclogites. On the other hand, behind the subduction zone, or sorry, not behind the subduction zone, but behind the trench. So behind the trench, you have the arc, and in the arc, basically, you experience, or the rocks experiences elevated temperatures at moderate to high temperature. So a moderate to high pressures rather, leading to a distinct group of rocks such as amphibolites, granulites, and maybe some eclogites at deeper levels. So that is how it looks like. So sorry, this was first recognized actually by Miyashiro in Japan, of course. So the Sanbagawa Ryoke Belt, Sanbagawa Belt represents the IPT rock. So in the field, you'll see pillow lavas. So these are basalts with clear lava flow texture that's been subjected to blue schist phase sheet metamorphism. So that's quite interesting. And then it's juxtaposed. It's a belt basically that's been juxtaposed sorry, juxtaposed to Barovian type zones, basically. So high PT plus low intermediate PT. That is the definition of a paired metamorphic belt. And paired metamorphic belts, therefore, are characteristic of subduction zones, meaning you don't see them anywhere else. In no other tectonic setting will you expect to find paired metamorphic belts. Right? So this is how they form. Basically, the high pressure, low temperature regions represent the subducting slab, and the high temperature, moderate to high pressure represents the volcanic front. Okay, and behind and beyond pala, slightly beyond the subduction front in some regions. Sorry, kasama ko ulit. Mali na ba ka na? Okay, so um, okay, so we discussed before, as I mentioned before, paired metamorphic belts are a marker of subduction zones. But actually, even if you don't have the high T, medium P rocks, just the high P, low T, low T rocks are enough markers of ancient or existing subduction zones. And why is that? Basically, yung high pressure, low temperature geothermal gradients that's required to form blue sheets and eclogites can only be generated if you have depressed geothermal gradients. And there's only one region where you can have depressed geothermal gradients, and that is along subduction zones. Okay, so because of that, we can use therefore these localities of blue schists and eclogite belts as a marker kung saan yung ancient na subduction zones. For example, here in the Urals, this represents the collision of the Laurasian plate with the rest of the Eurasian plate, Laurasia, well, European plate colliding with the rest of the Asian plate, Asian continent rather, Asian continent. This also represents the boundary of the Siberian platform colliding against the North China craton. So magkakaibang, you can see here basically yung markers, both ancient and present, for where the subduction zones once existed. And I would like you to focus in this tiny region, Philippines, of course. And there has been no officially or petrologically characterized, clearly characterized blue schist eclogite belt, which is very unaffected, very unexpected, because as you can see from Japan all the way to the south in Papua New Guinea, Indonesia, you see the belt. And we know for a fact that there's been subduction ongoing in the Philippine mobile belt since at least Eocene time. So this is a strange thing, uh, and this is not a function of these rocks not being in the Philippines. At least I suspect it. Uh, this must be a function of sampling. So wala pang nag-aaral basically, wala pa nakahanap ng blue schist and eclogi sa Pilipinas. And if you suspect that you have found one, let me know. Okay, yeah. So that would be a good contribution for geological studies in the Philippines. Okay, so that's dynamothermal metamorphism. So dynamothermal metamorphism basically are high pressure zones. So deviatoric stress plus temperature. So you end up with textures with basically characteristic of deep shear zones, as in subduction zones, strain contact aureoles, so contact metamorphisms, but contact metamorphosed rocks, that's been deformed because of the deviatoric stress, and you end up with orogenic belts, mountain belts. So orogeny, in during orogeny, you basically end up with multiple tectonic events. So compression, sometimes rifting na slide, and then compression, then rifting, and then you can also end up sa Philippines, for example. You also have strike slip faulting. So lahat ng to comes into play in orogenic belts. So you have multiple tectonic events and deformation phases. So itong deformation phase, we characterize this as distinct periods of active deformation with specific style, meaning with specific pressure directions, for example, which can be separated by periods of reduced or absent deformation. Okay, so metamorphic reaction events and cycles accompany itong deformation events na to. This results to what we refer to as polyphase metamorphosed rocks. So polyphase metamorphism happens when you have a rock experiencing more than one temperature or thermal climax, while monophase events are basically just single metamorphic event. So one thermal climax lang siya. Okay? So dynamothermal textures, because of the pressure that is present, or the deviatoric stress that is characteristic of this environment, um, yung kanilang characteristic texture is actually foliations. Yeah, so foliations, which may be primary or secondary. Primary meaning pre-deformation, meaning this could be either bedding planes, kaya this could also be secondary in the form of deformation, such as preferred orientation, either lattice or lattice preferred orientation, or uh, ito, DPO, dimensional preferred orientation. Okay, so we've already discussed when you form foliation. So this is an example of a bedding plane that during compression, basically, not na maintain yung layers na to. But usually, when you have deviatoric stress, this could be easily reworked into something more like this, like this, like this, etc., etc. If you have multiple minerals comprising a single rock, you usually end up with some minerals resulting kunwari quartz, resulting to this equigranular texture. Pero yung mass platy, yung anisotropic na minerals natin would tend to follow yung foliation, or would tend to form pala, or would tend to exhibit yung ating foliation planes. Yeah. And then these are melts, for example. So if you have melts in migmatites, for example, that may also correspond to foliation. Okay, so foliation. We've discussed before that there are different foliation types. It can be either cleavage, schistosity, or nisos. A cleavage is basically a fine penetrative foliation. So wala pa siyang growth. Usually this does not involve growth of new minerals. Schistosity, that is the one that involves growth of new minerals. And then nisosity is basically you have segregation into layers. Again, cystosity versus nisosity, wala siya actually in difference in terms of, hindi siya pala marker. Hindi siya marker of, hindi siya good marker of metamorphic grade. Not all gneiss basically are of higher metamorphic grade than schists. Okay. There could be many reasons why some rocks prefer a schistose foliation type or a gneissose foliation type. Okay, so this is a morphological classification of cleavage and schistosity. If you have microlithons, then you may just have spaced cleavage. So microlithons is basically this one. Basically, para siyang maliliit na domains that's cut or separated by foliation planes. Foliation planes in the form of cleavage, or foliation planes in the form of schistose foliation. Yon, gaya nito, for example. If wala microlithons, then you can have either continuous or slaty cleavage. Yan. What if meron kang crenulations na ma-recognize? So pag meron kang crenulations like this, yan, this is what we call crenulation. Okay? Ito naman. Ito yung crenulation. So this usually indicates a distinct pressure direction or a change in pressure direction. So for originally, for example, ganito yung stress, okay? North-south, basically yung stress. So that would result to foliation like so, horizontal foliation. And then, what if nagbawi yung stress east-west? Yan, pwede siya maging ganito. Magkakaroon ka ng crenulation cleavage. Okay? Yan. Ano pa? Okay. So this is just a volume change. For this one, you just have to remember yung some of the terms, but hindi ko naman kayo paparecognize it or hindi ko naman kayo papag-identify ng cleavage types or siguro yung mga ano lang. Is this a microleafan or do you see a microleafan? Do you see what texture do you see? Granulation? Mga ganun. Okay? Okay, so ito yung sinasabi ko kanina na if you have crenulation, usually that's a marker for changes in in stress direction. So for example, this is A to B. So originally ito yung stress mo. So the pressure is east-west. And then eventually, because of a change in pressure into something more north-south, you start deforming the rock until eventually you end up with this this type of foliation. So completely wipe out na yung original foliation natin. And what does this say? Basically, what this diagram tells us is that with increasing deformation, the pre-existing foliation can be erased essentially. So development of granulation cleavage is a function of temperature and intensity of secondary deformation. With increasing intensity of deformation, obviously, the new foliation will eventually follow yung stress perpendicular or yung direction perpendicular to the stress. So, yan. Okay, so yung kaninang crenulation, ito yun siya. Yan. Okay, this is for just fine grain phaelite versus schist. Okay, and then lineations. We've already discussed lineations. So basically, lineations occur or lineations may happen when you have sigma 1 equal to sigma 3, sigma 2 rather, and both of these are less than or greater than sigma 3. So the difference again is that when you have foliation, these are planar arrangement of the minerals. Lineations is the linear arrangement of minerals which signify or which are parallel to sigma 3, always parallel to sigma 3, unless at least for stretching lineation. So if you have minerals that are stretched or that are preferentially elongated in one direction. Okay? Pag random lang yung mga elongate mo minerals, then there's no linear, there's just foliation. Okay? So this is an example of that. So you have here, ito for example, you can think of the black minerals, which are basically isotropic. These are garnet grains. And then you have elongate minerals, for example, amphibole, which exhibits lineation like so. And then at the sides, you can see yung foliation planes naman niya. So again, lineations, you can only describe this in the plane or in the you can only notice or you can only note the direction of the lineation along the foliation plane. Okay, so this is how lineation looks like. So you imagine a straw. So this is the lineation direction. If you look at the sides, it's foliation. Yan yung foliation na ninonote natin. Ito naman yung lineation natin. So this is the alignment direction. Paano pag gagawa ng thin section? Pag gagawa ka ng thin section, it should be parallel to lineation. What if you have only foliation but no lineation? This is how exactly it looks like. It's highly foliated, but as you can see, the minerals, the elongate hornblende minerals does not exhibit a preferred orientation. So foliation but no lineation. Okay. Yeah. Other dynamothermal textures include, I think for this one, I think i-discuss ko na siya dun sa continuation lecture. So, you have 2 lectures. After this one, may isa pang pre-recorded lecture. Both links will be sent to you. Okay, so see you on Tuesday next week. I'll be back from the field on Sunday. So see you on Tuesday next week. We will have a quiz on this whole chapter 3, okay, textures. And then actually tapos na tayo after that. After this meeting, after this week's meeting, tapos na tayo sa chapter 3. So we'll finally move on to the last chapter, which is actually good. That gives us a lot of time. That gives us a lot of time kasi matagal yung um, or medyo mahirap, hindi naman medyo complex lang yung coverage ng chapter 4. Okay. Thanks, guys.